As I'm sure you know, you've probably made things like this, little animals. This is a crane, and it's a fun exercise. You can make these sorts of things. They look cool. I have some others. I'll get one. Like, if you make modules, you can interconnect them. You can make stuff like this. Pretty cool. Um, what I'm gonna do though is unfold this, and you might find this interesting. If you've unfolded it, you'll notice the creases make these sorts of patterns, and the patterns that they make are somewhat interesting, and there's ways of describing them. So what I'll say is this is what it looks like when it's been unfolded. We call this thing a crease pattern. And so if you were to make these creases and then fold it together, you would be able to get the crane. It would look something like this when you're all done. Uh, and so I'll show you. Is my slideshow working?
Yeah, showing up for me. Looks good.
Okay, cool. So there's the crease pattern. As you see, there's two different ones. So normally, when you have a crease pattern, it will give you instructions on how to fold the base. And so the one on the right will you'll be able to fold this from the one on the right. And from there, it's kind of your job to finish, and you make your folds to shape the crane. And once you're done shaping it, it looks like the crane. Um, and so the one to the left includes all those folds. And the point is, once you have those folds, the crease pattern becomes a lot harder to read. And it may not make sense how to make the folds on the crease pattern. You know, those triangles that go to the head. It's not necessary because you can figure out how to shape it yourself. And so you go with the thing on the right. And another thing you may be wondering is that there's both red and blue lines. And so those are the two different types of folds you can make. A mounted fold would be a fold that looks like this. So when you look at the paper, it makes this kind of mountain-like shape. And a valley fold would be when you look at your paper and it makes this valley shape. And when you arrange these in a particular way, you get the crease pattern. And so if I fold like this, then I have two mountain folds. Then if I fold like this, then I should have a valley fold. And the idea is when you flip your paper, all your mountain folds become valley folds, and all your valley folds become mountain folds. And you'll see that's important.
Wait, sorry, to make sure I understand. So the claim is that the two different crease patterns you have on the screen now, the left and the right one, the right one is simpler, so it's like somehow a minimal pattern, but the claim is that you can uniquely reconstruct the more complicated one on the left, beginning with the one on the right? Is that it?
No. So you can't uniquely reconstruct it. Typically, when you look up crease patterns for different things, you'd get ones that look like the one from the left. And so you get something like this. And then it's up to you to use your artistic skills to create the thing on the right. And yes, you wouldn't be able to exactly reconstruct it if you're not given these folds. But typically, once you reach this point, you're able to figure out what you want it to look like. Maybe in this case, it doesn't make as much sense, but in more complicated models, you'll find that you've arranged all the flaps such that they're designed to make specific features.
Okay. So there's strictly less information in the minimal one, but you're supposed to be able to infer what to do or something given the smaller one, I guess.
Yes. So this has less information. Then once you make these folds carry that information, and then this also carries information that you use to make the final thing.
Good.
Okay. And so these work these mountain valley arrangements in general give you the instructions to follow that minimal pattern type thing. So as I'm going to show you on the next slide, they can get a little bit more complicated. Um, and so this is called Vaijin 3.5. I find it cool because this one in particular, you might see lots of things in the pattern. You'll notice that all the scales, they happen to have spots on the crease pattern that map to them. And so this is more of just, I'm not going to show you how to make this. This is just, I'm trying to show you how you can make all sorts of things using these crease patterns. I'm not going to move on to the next slide. I'll do an exercise now that will demonstrate one theorem that you might find. So if you take your paper and you put a dot in the middle, it doesn't have to be exact, just somewhere on the paper. Put a dot on that paper. And then make folds that pass through this dot. You can fold like this, go like that. But whatever you do, just all of these folds should pass through the dot.
Okay.
So this is fine. You can do that. They can basically be whatever you want. Just fold through the dot. And I'll give you a minute to do that. Okay.
Okay.
Have you done it?
After doing that, am I supposed to leave it folded or unfold it to see the pattern?
Okay, so yeah, I'm going to ask you to unfold it now. And what you should do is count the number of mountain folds you see and the number of valley folds you see. So in my case, there's 1, 2, 3, 4 mountain folds, and there's 2 valley folds right here and right there.
Okay, I made too many, but let me. I have to go through and label them. Let's see one sec. I have way more mountains than valleys. It looks like.
Yeah.
Did I do this right? 1, 2, 3, 4, 5, 6 valley and 3 mountain. Did I do that right? Is that an allowed combination?
That isn't.
That is not allowed. So I did something wrong, I guess.
Yeah. You might want to show the paper. That.
I don't know. I tried labeling them, but I think I may have done something wrong. It's kind of hard to see from the camera which is mountain and which is valley, I think.
I think I can see. Oh, okay, this makes sense. So one of your valleys is it going through the point in the middle that you made? Yeah. So that's. I think that's
right.
it.
Yeah, sorry. Yeah. I tried to, and I think I missed the point with one of them. Yeah, I think you're right.
Okay, so I'm going to make a table. And so if you get rid of that one valley, you'll find that you had 5 valleys and 3 mountains. And in the one that I made, I had 4 mountains and 2 valleys. Everyone else who's attending the talk, you should tell me how many mountains and valleys you got when you did this. I think if we had some more data, you'd be able to see the pattern much more clearly.
Is anyone else doing it? Alicia's here. I don't know if she did it.
I mean, I can tell you like the pattern if you want, but it just won't make as much sense if you haven't worked through it.
Okay. Skygear does not have paper, apparently. I don't know if...
What are we doing? I just joined.
We're folding paper and counting mountains and valleys. If you would like to participate to give us more data. We only have 2 data points.
Oh, yeah, I think I know the answer to this. I think it's like +2 or something like that. Right? There's like, maybe, I don't know.
I've already, you've seen the talk I gave in math club, so you know the conclusion.
Yeah, this is just a repeat. Okay, I'm gonna listen.
I'm just gonna make another one. So this one has three mountains and a valley. So this is what it looks like. So you want to take some guesses as to what the pattern is?
Um, they seem to differ by 2, but it's not consistent whether it's always what the valley number is greater.
Absolute value m minus v equals 4.
So I'll show you, right? So this is what it looks like. There's three mountains and a valley. So if I flip the paper, now there's three valleys and a mountain. They depend on your frame of reference. So you can have a mountain minus valley or valley minus a mountain, because when you flip your paper, all you're doing is just saying, okay, now these are valleys and these are mountains. And so the difference, it looks exactly like this. Yeah, they always differ by 2. And I'll show you why. Which is, let's take this pattern. And normally you don't do this because normally you just fold paper in origami. But I will cut it to show you something, which is, now we can see the cross section. And it looks something like a polygon. This is a quadrilateral. And so when you fold it, it still is a polygon with angles. So you'll see that this angle is going to be 0 once it's folded. This one is 0 once it's folded. This is 0, and this is 360 once it's fully folded. And so in a polygon, the angles have to add up to 180 times n minus 2. So in my case, it's a four-sided polygon. So you'll find that it's going to be 360 degrees. That's what they should add up to. And the other thing is that in this case, this valley fold contributes 360 degrees. All of these mountain folds contribute 0 degrees to this angle. And so if you say that, then you say, okay, 360 degrees times your number of valley folds is going to be equal to this. And the number of folds you have is equal to the sum of your mountain and valley folds. And so you get 360 times this is equal to 180 times. And so if you do the math here, it goes, I think I messed up. It's your number of mountain folds plus the number of valley folds minus 2. This is the n minus 2 term. I don't know why I did that. So, because this is just n. And so, this is 2 is equal to, what am I doing?
Well, can I ask question?
Yeah, sure. Ask questions.
Okay, good. So I feel like I asked you this perhaps in math club.
Yeah.
But the question was drowned out by Jason saying something or something like that. Something silly. I'm assuming n is the number of sides of the polygon, if I'm not mistaken, right? So I might just be being a little bit stupid, but no matter how you fold, the claim is that no matter how you fold this polygon, the number of mountains plus the number of valleys of any fold, any sequence of folds of this polygon, the sum of the mountains and valleys will equal the number of sides. That's the claim, right?
Yeah.
Wait, why?
So when you fold your vertex,
right. Wait, actually, this might kind of be trivial.
As you see, when you fold your vertex, each side of your cross section would be governed by one particular fold. Because the only time your paper can have a bend in it is when you have made a fold. Otherwise, it's fully flat, so it can't make a new side.
Mm-hmm.
Um, and so
Also,
all
for
you
the
have
sorry to interrupt. For the algebra on the board, before I forget, you dropped a v on the left, so it should be 360v is 180 times the quantity m plus v minus 2, which would then be 2v equals m plus v minus 2, right?
2v 2v equals m plus v minus 2. Yeah. And so now you solve the equation. So v is equal to m minus 2. And so v minus m is equal to negative 2. And so whatever these are, if I flip the paper, as I said, I can swap them. And so that means that m minus v would also equal negative 2. And so you can multiply both sides by negative 1. And so you'll get m minus v is equal to 2, and v minus m is equal to 2 as well. And so you can say this more concisely by saying the absolute value of their difference is equal to 2. And this is true in any particular situation where your folds are flat. So we would call this thing a flat folding origami because once you make all your folds, it's completely flat. Whereas there's other things that once you make all your folds, it's not flat. Does anyone have questions?
Related to Alicia's question, so you've shown that the difference between m and v is constrained to be 2 in absolute value, but is it clear that you can have any sum, so you can get an n-gon for any n by doing some series of folds?
Yeah, so no matter what folds you make, like this one's gonna be a larger n. And so you can make all these folds and you can still cut the top off to make your polygon, and you still have some sort of polygon once you do that. And so
yeah,
and
so, yeah, it's clear that it's always a polygon, but is it clear that for any n, you can cook up some folding pattern which would give it n-gon, or are any of the n forbidden? Like, could it be that, oh, you can't get a 17-gon or something, like some are not allowed, or are all n allowed?
Alright, so if the difference between the mountains and valleys is 2, I would imagine that you would be able to get everything, right?
That's what I would think as well, yeah, because you have two variables and there's one constraint between them that the difference is fixed, but the sum is free. So I would have thought the sum can be anything, unless there's something I'm missing.
Are there two numbers that... So I'll go to your example. Are there two numbers you can think of that add to 17 and the difference is 2 and they're both integers?
Oh, yeah, that we can do. So how about... let's see... Well, okay, I can solve this in mathematically because I can't do this in my head. So, okay, so solve m minus v equals 2 and m plus v equals 17 for m and v.
There exist integer solutions for m and v. If no, then you cannot make a polygon with 17 sides using this method.
Yeah, oh, you're right. That's the issue. The integrality constraint can screw us. Yeah, good. So yeah, if you solve m minus v is 2, and m plus v is 17, it wants to make them half integers, which is bad.
I believe 8 plus 9 equals 17, and so if these differ by 1, and so if you subtract 1 from this and you add 1 to that, they would differ by 2, so it would be 7.5 plus 9.5. These are the only ones which you could do that would differ by 2, but these are not integers, so you could not make a 17 gon.
Good, okay. I see, so there are constraints. So there's only some allowed n, you say?
Yeah, there's only some allowed n, yes. This particular constraint applies to everything that is flat foldable. So right now this is not flat folded, but if I fold this is completely flat, and then it only exists in 2 dimensions if your paper was infinitely thin. And so this this particular condition would only apply in that case. If your folds are not flat, like in this one, this clearly isn't flat at all. This condition doesn't really matter.
Is it topological though? Like if you fold something flat, I mean the difference between folding something flat and folding something which is topologically a sphere is just that they have different Euler character because the sphere has positive curvature. So is the difference between V and M just fixed by the topology, like whether it's like say flat or a torus or a sphere, or is it something else?
Okay, so it's a little bit more complicated. There's two cases. In one case, the case where you made your dot and you cut the top off, right? You had a single vertex, which was wherever you placed your dot. And in that case, if this condition is met, you know for a fact it must be flat foldable. However, I'll show you an example in my slideshow, which it's necessary but not sufficient. So you can try to make this if you want. No matter how you arrange your mountains and valleys on that particular crease pattern, you are not going to be able to fold it flat. I don't know if I answered your question though. I didn't really understand.
It's along the right direction. I think you've given me a hint to the answer for the question, but you'll probably address more of it as you go on, I guess.
Yeah, so there's other conditions that exist, but I don't want to spend too much time talking about it. For example, if you look at the angles in a vertex, so I will make another one of them. If you look at the angles of this vertex, this one, and this one will add up to 180, and so will this one, and this one. So if you alternate the angles that you add up, they add up to 180. There's a few other conditions, but you can know all the conditions and still not be able to tell if something with multiple vertices will fold flat. And I don't know, does that answer it any better?
Yeah, it's related. I mean, it smells very topological, right? Because I mean, it's based on the statement that angles of polygons add up to some fixed amount, which is true on a flat surface, but would be false on a sphere, for instance. So the one that you showed me, which was not flat foldable, was topologically a sphere. And as we know, triangles on a sphere don't have to add up to 180 degrees. They can add up to, if you go from the North Pole down to the equator or something, it can add up to 270 or something. So, okay. So it seems like it's going to be related to topology somehow, but I'll let you go on because, I don't want to derail things with my esoteric questions.
No, it's fine.
Wait, Eashan.
Yeah.
You win for like even numbers though, right? Like you were talking before about how you couldn't find two natural numbers m and v such that n plus v equals n and the absolute value of n minus v equals 2. But for even n, you win. And I conjecture for odd n, you always lose, right? Like in the sense that you can't find two even integers with the two properties that I just stated.
Yes.
Or not even integers. I suppose they'll be natural numbers, right?
This is true.
Yeah, okay.
I'm not going to... I don't think... This isn't the focus of the talk, but yeah, this is true. You cannot make an odd number that satisfies this condition. Because, to think about it, if they differ by 2, that means that if you take the average of them, that's some number. And then when you add it up, it's
exactly. So minus 1 plus 1.
Average, it could be expressed as an even number.
So triangles are bad. And
they're not bad. It's just that you can't make
it. They don't satisfy this property, right?
Corresponds to a flat foldable origami.
Flat foldable. Okay. Awesome sauce.
Okay. Yeah. But even in the slide that I have up, the triangle is not really related to the vertices. You can see all of the vertices are marked by the intersection of 4 different pieces. And so you could make your quadrilateral cutouts, but it still won't work. If you want to try that, you should. I'm going to move on though to something else. I want to talk about constructions. So I'll get some paper and we can talk about that. So I'm going to ask, do you know how to fold a piece of paper into thirds? How would you go, if you have this paper, how would you go about making it into thirds by folding? So if you're making a letter or something, how would you make it get folded into thirds?
I don't know of a systematic way that I just start at the bottom and then try to fold it up until eyeballing it looks like it's about 2/3 and then fold the top down. There's probably a better way.
Yeah, so this is true. This is actually a valid way of doing it, technically speaking. Except okay, so if you fold your letter like that, it'll be good. You probably will manage to put it in an envelope with no problem. But there's a way of doing it exactly with only one fold at a time. And so this is important because if you want to make more complex things, there's some constructions that you would only be able to make with multiple folds. And so doing a two-fold thing would be slightly overkill for something that can be done with one. And so I will show you the construction right now. So if this is your paper, I'll pull up the axioms or the rules of how you can fold a paper quickly. So these are all the possible single fold operations you can do. You probably shouldn't read through all of them. I think you'll figure out, like, most of them are intuitive, but what you want to do is you want to fold your paper in half. So you start and you fold it. So let's do that. Yay. So now the paper has been folded in half. And then we want to make a line connecting the two corners, which we can do. So I will do that right now. Okay. And the last thing we want to do is make a fold that connects these 2 points. So that can be done as well. You might want to follow along and make this yourself. So just make sure this is good. Okay. And so now this point, I'll prove this to you afterwards, but this point is exactly at 1/3, 1/3 if you look at the coordinates of your paper. And so you can make your paper into thirds like this because this edge is square to the rest of the paper. And so you can fold along such that this edge aligns and this other edge of your paper touches this point which we have just created. And then you do this the other way as well. And so once you have done that, your paper has now been folded into thirds. And so, are there any questions before I prove to you that this is true? Okay, I'll show it to you then. So, if you look at the paper, it has some height, which I'll call h, and it has some length, which I'll call L. And so, what you do with this is you have effectively bisected this line segment that makes up the edge of your paper. And so this has coordinate h/2. And so when you construct this line, it has an equation y equals h/2, because this is a y-intercept. If we let this be the origin, y equals h/2 minus h over. So your rise over 1 is just going to be negative h. It actually falls, and your 1 is L. So it's negative h over L, and that is multiplied by x because it's your slope. And so the other line you make looks like this. And so y is equal to your entire thing. Oh, this should be h over 2L because you only go down halfway through the paper. It should be h over L times x. Are there any questions right now? No? Okay. Is my audio working fine? Is all good? Okay, cool.
Yeah, I can still hear. Good.
Yes,
yeah,
it is.
so good.
Yeah, so what I'm going to do now is find the intersection point of these two lines. So I'll do that. The way you do that is you set these equal to each other, and then you solve for x and you solve for y. And that'll give you whatever x is and whatever y is. And so you have this is equal to this. Okay? And so this is when you add these two together, you get 3 halves h over L times x is equal to h over 2. And so you can cancel out this, you can cancel out this. And so you get 3 3 over L is equal to 1. And so L is equal 3x over L is equal to 1. And so 3x equals L. L is equal to x over 3. And so this is 1/3 this way. So if you wanted, you could even fold your paper into thirds like this using the exact same thing. And so this is 1/3 of the paper as well. And so you can make grids using this method. And so since y is equal to h over L times x, if you plug in what we have already solved for, you should get that y is equal to h over 3. Okay. Are there questions? Oh, shoot. I messed up on the algebra. Okay. Are there any questions now? Okay, cool. So now I'm going to ask how you would generalize this. So let's say, great, we can fold thirds. Now I have a paper and I want to fold it into fifths. So this is not, I'm eyeballing it, but we can make these exactly by folding the paper. So let's say you want to make these. How would you do that?
So just to clarify the question, what are the in constructing a partition into fifths? What are the allowed moves? Are we only allowed to do folds that go between corners or from one corner to the half height of the other side, like we did before, or are you assuming you can pick like any marked point on the side and make that fold?
Yeah, you can pick any operation that I have on my slide actually, but you don't need to. As in, you could do with the exact same operations that I did to this paper, you could fold fifths. But if you're inclined to, you can use those if you want as well. I would be interested in hearing a solution that uses that too.
Could you could you be able to fold the paper in in quarters? Like start off with that first, and then for like each of your quarters, you can like fold it like a diagonal, like for each of them, so it goes like something like this zigzag shape. And then if you get your two corners, and then like I don't know how to describe it, but I drew like a diagram in the maths talk discussion, kind of show like some of the folding lines. But the point is that if you can fold it in quarters like along this way, and then for each of those quarters you can match, like you can fold to get like one of the corners out to the other corner for each of those sections to draw like zigzag folding lines. And then you do the same thing for the top corner and then the bottom corner like this, and fold across like that. Then you can draw like a folding line that intersects all those zigzags. And then the point of like the highest, the point of like the intersection that's like at the highest on your paper, like that kind of shows like, okay, if you can fold the paper along like on that and then keep on going, then you can split your paper into fifths. I think I don't know if that made sense.
I'm going to check the diagram that you sent.
Yeah, so in the diagram I sent, I
see.
Yeah.
Okay. So this is, I think that works. It's a little bit different from what I will show, which is, okay, so we can fold our paper into half. The quarters thing is good. That's exactly what I'm going to do as well. So if you have your paper like this, you can fold it in half. You can fold it in half again. I don't think it was showing up in my camera frame, but okay, now there's quarters. And so you can fold your same diagonal as before, which is still valid. Okay. So you can do this, and then once you've done this, you can fold from the point your quarter, and then you can do the exact same thing we did with third. So you make your line that goes from here to here and here to here. This intersects at fifth. And so you can make your other construction folds. So you can fold like this, and then once you fold like this, okay, I'm going to write down what I just did. I think it might be hard to follow. Okay, so this is halves. Okay, then I made a fourth. So okay, and then you make this line, and you make this line, and this makes fifth. So are you starting to see a pattern in the method that I've used? As in, if you were to make a slight modification to my method, would it be possible to fold the paper into however many parts you wanted? So, I don't know, would it be possible to fold it into 983 parts if you had the time and the energy and the drive to do it?
Well, it's not obvious to me, because there could have been some number theoretic constraints or something, right? It could have been that thirds worked and fifths worked and fourths worked or something like that. But I mean, maybe you can get any integer fraction, but it's not immediately obvious to me that this lifts to anything, right?
Okay, that's interesting, because I'll show you that it actually does work. Like, if you wanted to, you could. Now, the method I'm going to be showing is not at all the most efficient method. If you wanted to do this, you could do it with way less folds, but this just shows it's possible relatively easily. And so we've shown that our method is true for n equals 2 because you can fold your paper into half, right? Okay, so we have halves. So we know it's 1. We know it's... Okay? And so now let's think about it for the case of any n. So if you have your paper, whatever this is, it's this point, we could say this is equal to h over n. So maybe this is halfway through the paper, maybe it's a third of the way. Whatever it is, n is some integer, which is kind of important. But once you have n being some integer, you can construct this fold, and you can construct this fold. So y is equal to h over L times x. Use the same equation that I made last time for this, because it's still the same thing. And the other one is now slightly trickier. The y-intercept is no longer h over 2. It's h over n. And the slope is now h over n. That's the change in y. The change in x is L. And the change in y is negative because it goes downwards. So it's going to be minus h over n times L times x. And so you can set these equal to each other. This is equal to this. And so if you add this up, if you rearrange this to solve for x, you should be able to find what x is equal to here. H over L times, this is 1 plus 1 over n, I think. 1 plus 1 over n, and so that's equal to this. And so you can rewrite 1 plus 1 over n as n plus 1 over n. So h over L times n plus 1 over n is equal to h over n. So you can cancel these out. And so now there should be an x here. I did that last time as well. And so now you get that once you solve, you'll get that x is equal to L over n plus 1. And so once you've done that, that means that whatever you had, now you've been able to add 1 to that. And so this means that you're able to induct now. So if it's true for n equals 2, and it's true for any n, if it's true for n, then it's true for n plus 1. Then true for n plus 1. Then you'll find that if you use induction here, you'll be able to get any n you want. Is there any questions? No, okay. So once you fold it for n equals 2, you can fold 3, 4, 5, 6, 7 like that. There's faster ways of doing this. So let's say if you wanted to make 7s, you probably would not go and say, okay, I'm going to make 2, then I'm going to make 3, then I'm going to make 4, 5, 6, then 7. So I can start by I can make thirds, so I go from 2 to 3, and then I can bisect my thirds so I can go to 6, and then I can go to 7. And so I actually save a lot of time if I construct sevenths like this, for example. And as I explained with fifths, you would not go like that. You would just go straight, okay, 2, then I'm going to go to fourths, then I'm going to go to fifths. And so you'll have fifths made with one less step. You skip 3 steps if you make sevenths, for example, or 2 steps, these two. Okay. I'm not going to. I haven't figured out a way in general of how many actual steps you'd have to take if you did it in this most efficient way. But that's an interesting problem. You might want to work that out if you want to do that. Are there any questions right now? Okay. I'll get some paper. How's the time? What's the time right now?
Ooh, I'm wondering if there might be like another way of doing this that doesn't require induction, perhaps.
I
You
was
know, if
like,
there's like,
what?
oh yeah, you go on.
No, you go on. Never mind.
Oh,
Finish.
yeah, because I was wondering that maybe what we can do is like similar to the diagram that I drew before. Like we could imagine, like we could get this like rectangle here and just like put it on a grid and then pick one of the points as like our origin, like one of the corners, sorry, as like our origin, and then like then we can describe the other points in terms of like other like x and y coordinates, and then yeah, then we can like perhaps just like pick a point on like one of the sides of the figure, and then like let that like basically draw a line that basically cuts through that, and then cuts through one of the axes on the grid, and then you can also draw the line going from the diagonal line going from the corners. You can just imagine that as like some like line, and then also the other previous line you drew just as another line, and then just find the point of intersection, and then it's just like, you know, solving like a linear problem basically. I think that might be a better way of doing it perhaps. I'm not sure. I'm just only thinking about this like conceptually. I haven't haven't done it like
That's-
computationally. So
That's reasonable because I just showed it to you, but I'm not. I didn't understand what you meant about like you were describing some sort of method of construction that you wanted to use. I didn't really understand that. Could you?
oh yeah. Could I? One second.
Okay, I can.
I'm just gonna go on. Yeah, I'm just. I'm not really good at describing like with words. So I'll just draw a diagram. I'm just gonna pull up co-create shared whiteboard, and then maybe like share my screen.
Okay.
And then hopefully like draw on it. I guess hopefully it doesn't like cause too many problems.
Okay. So, yeah. I'll look at that once you have made it. I want to see that. Seems pretty interesting.
Yeah, I can go through with it now. I'm just hoping that it doesn't like like things just don't lag, and then all of a sudden just
It's fine.
Can you hear me, by the way?
Yes, I can hear you fine. Yeah, the screen's lagging a little bit.
All right. Well, maybe then your idea is better. Then I'll just you can just look back on it later after like I've drawn it. Then I can just send some pictures.
Okay, cool.
rather than like doing it live, because then it would,
Yeah.
yeah.
So, yeah, as I was saying, induction is not at all the most efficient way of doing it in reality. In practice, you can skip a lot of steps using this type of thing where, okay, I can fold thirds. Okay, whatever n I have, I can do n plus 1 and I can bisect n. So I can double n and I can add 1 to n. So I can do more than just. I can get to a particular thing much faster by also using the ability to double n, rather than just only adding 1 to n. And so, yeah, that's a fun problem to work out if you want to do that.
Wait. Question. So we're trying to prove the claim that the intersection of the line y. Okay, the intersection of the line y equals h over l times x, where h is the the vertical distance between the left corner, or the corner right here, the left hand side corner, and the right hand side corner, otherwise known as the points 0, 0, and 0, h. That's what I'm defining h to be, and l is the value, like the width of the paper, if you will. Like it's the distance between the point 0, 0 and l, 0. Sure. Okay, whatever. So we claim that the point of intersection, or the y value of the point of intersection of the lines y equals h over l times x. And I think I had this written down, but I've closed my book at this point. So you have it on the board, I'm pretty sure. Y equals h over n minus h over n l times x. The y value of the intersection of those lines will be h over n plus 1, right?
Yes.
Yeah. So wait, why didn't we just like prove that? Like, why can't we just construct like, why can't we literally just find the point of intersection between the lines y equals h over n minus h over n l times x?
Exactly.
Like, well, why is induction necessary? Like, this is true for any like natural number, right?
So
minus 0. Like,
okay.
This is true for any n and n minus 0.
Okay. So the reason why is because we cannot just construct h over n automatically, right? If I have this paper, we haven't yet proven that I can get to, like, let's say I wanted to make fourths or something, and I can only add 1, right? So we haven't yet proven that
Okay,
I
sure.
can
Yeah.
get to thirds, right?
Fine, yeah, this is true.
So the claim is not just where these lines intersect. The claim is using these intersections of the line, can I actually fold the paper into however many parts I want to?
So you have to. What is the difficulty? Is proving that, like, what, that you have a line of the form y, like, you have a line of the form y equals h over n minus h over n l times x in the first place? Is that like the difficulty?
Okay, so let's say that I'll give you a more concrete example. So if you look at n equals 4, we're trying to get to n equals 5. The difficulty from getting to 4 to 5 is not a problem, right? This line tells us how to do that.
This is
But
true.
the issue is, how do I get to 4 from nowhere? Like, I can't just automatically divide my paper into fourths. I have to somehow construct.
Okay, sure. This is true. Like, this is induction. I get it. Yeah, fine.
Yeah. So that's why induction is necessary to prove this.
Yeah, you want to prove that the 4 cases even like existent in the first place. That's fine.
Yes. So.
Or is correct.
Yeah. Okay, cool. I'm going to show one more thing that you can do, and then I think I'm going to wrap up. So the paper is going to come back again. This is an interactive exercise, so I encourage you to get paper out. And I would recommend that at least one edge of your paper is flat like this. It might be useful. And so somewhere in this general area, like the lower part of the paper, close to the middle-ish, keep a dot. So I have a dot somewhere in the lower part of my paper, kind of close to the middle. It's not at all exact, but it doesn't need to be. And then what I will say to do is, this bottom edge of the paper should be folded towards this point. So you can do that. Doesn't matter how you do that. This works. This works as well. You can do this as many times as you want. Actually, I encourage you to do this many times so that you can see what shape the folds make once you have made them. So there's all sorts of ways you can do this. The only constraint is that this bottom edge must touch this point once you have made whatever fold you make. So do that a few times and let me know what you believe the shape looks like once you are finished. Okay. Once someone has done that, just speak up, let me know. This is roughly what it looks like once you do it.
Yeah, it looks like tangents to some curve coming down. I don't know what curve, like a parabola or catenary or something, but it looks like an envelope of tangents to some curve passing through the point, right?
Yes. Okay. This is valid. Yeah, that's exactly what it is. It's an envelope of some curve, and you are about to find out what that curve is. Okay, so we have some point, we have some line, and when we fold this line to this point, once you make your fold, there's some point on this line, this point in particular, that once you put this point here and you fold it, you could make your fold. So I don't think I said that well at all, but I have a point. This point makes some segment with the point that we made earlier, and once I make the fold, I create a perpendicular bisector to this point. So it looks like this. Does that make sense? Okay. So once this is perpendicular to this, what you can do is, well, I can do this as many times as I want. So perpendicular, what am I doing? I messed up with that. Okay, so this, you can do that, and you can do this for all the points on this line. Your paper is finite in this direction, so technically can't do every single point that would exist on a line, but you can get a good enough approximation, and so that's kind of the point of this exercise. And so you can do this, okay, perpendicular bisector. And so once you make all of these lines, you'll notice they satisfy a property, which is that whatever the distance between this point, this, okay. Okay, let me think. These distances are the same. The distance of a point on whatever curve you're enveloping. So whatever this envelope is, the distance from some point on your envelope to the center is the exact same as the distance from that point to this line, the bottom of your paper. So now I'm going to ask, you might happen to know a particular curve that satisfies this property.
Is this a parabola with like the directrix or something, or tractrix? I forget. There's some word for this thing where there's the line that everything has these equal points from, something with an x in it. I don't know, but I think it's a parabola, right?
Yes. this is a parabola, and so the bottom of your paper is your directrix. This is your focus, and the distance between your focus and directrix is the same for any point on this curve. And so
I can never remember the word directrix because I confuse it with dominatrix or something. But good, thank you for reminding me.
okay, so that's a parabola. There's ways of making all the conics actually, but I want to wrap up here now. That could be an exercise to do. I don't know. I could talk about solving equations with this. That might show something. I don't know. Um, yeah. So I wanted to talk about that, but I think this might be a good time to wrap up because it's been a while. But are there any questions?
I'm curious about the. Oh, sorry. There was another question.
Yeah. What's the question?
I was going to ask that I was curious about the equation thing that you were about to say, but once I started saying that, someone else unmuted, so I didn't know if there was another question. If there's another question, they should ask that first because I'm just curious.
You should ask it. Whoever the other person is.
Okay, I guess they disappeared, or I scared them away, or something. Okay, or I hallucinated.
Yeah. So I don't know where this other person is, but I can show it to you quickly. You might imagine if we can construct a parabola, we can solve second degree polynomial equations, right? I think that might make sense because you could solve a polynomial equation by finding the point at which a line intersects a parabola. And so you get your roots of the equation like that if you want to do that. But as you know, our envelope is not exact, and so we could do it, but we wouldn't get the exact thing. We would not get the exact solutions that we are looking for. But there's a way of doing that, and I think I'll leave that as an exercise actually, or I could show it in the math talk discussion because I remember it, but I don't want to mess up. I don't know the proof that it's valid, so I don't want to show it.
Okay, good. Well, yeah, I'll take a look if you post it or something. It seems kind of interesting, though. I mean, it's reminiscent of like compass and straight edge constructions or something like that. It's like what can you build? What can you not build? Like, is there any example within this set of construction rules analogous to how, say, for compass and straight edge, you can't trisect an angle, or there's certain things that you can't construct because Galois theory forbids it or something? I mean, we've seen some examples of that here, where, for instance, you can't get odd-numbered n-gons when you cut, at the point in the beginning or something like that. But is there anything else like that there's an interesting thing that's forbidden with one of these paper folding constructions?
Okay, this is cool actually. I will. You know what? I'll share some basics. So there's three problems you might know of. There's three like big problems that cannot be done with compass and straight edge. So that is angle trisections. There's angle trisection. Then there's doubling a cube. And then there's squaring a circle. And so, yeah, let's say we wanted to trisect an angle, right? With compass and straight edge, you can't do that. I'm not going to show the construction here, but there's a way of doing it with the constructions that I have shown you. So you can trisect an angle using this. And you also can double a cube. So if you are confused by what doubling a cube means, it means, let's say we have some cube. This cube has some volume, which we'll call V. And so we want to make a cube that has a volume 2V. And so and look something like this, I guess. And so this cube should have exactly a volume twice this cube. The way I've drawn it is not to scale. This would look like it has probably 8 times the volume, but I think you get the point. And so the brief explanation is that compass and straight edge can solve quadratics. And so the problems you can do with compass and straight edge are all reducible to quadratic equations. And the problems you can do with origami can be reduced to cubics. So angle trisection can be reduced to a cubic. You have cosine cubed of something minus cosine of something equals cosine theta over 3. And there's another theorem that says that for an angle to be constructible, its cosine and sine must be constructible. And so why you can solve quadratics with compass and straight edge, and you can solve cubics with origami. It's a little bit beyond the scope of this talk. You need Galois theory to show that. But yeah. Squaring the circle cannot be done under the axioms that I've shown you. That's the only one of these 3 problems that you can't do. So as a reminder, squaring a circle means, okay, I have some circle with some area, and now I want to create a square that also has the exact same area as this circle. And so the big issue you have here is you need to construct a side with length square root of pi. And that cannot be done because pi, as you might know, is transcendental. And that means it's not the root of any polynomial equation. And so when these constructions allow you to solve polynomial equations up to degree something, that doesn't matter if you cannot solve a polynomial equation to get pi. And since pi is transcendental, so is the square root of pi. Does that answer your question?
Yeah, that's interesting. So, I mean, is there... it's not at all obvious to me why you should be able to do roughly field extensions in Galois theory with cubics using the paper. Like, I can kind of understand why compass and straight edge is letting you do quadratic field extensions like roots or something like that, because the compass is letting you draw something with a fixed radius, so it's like a circle which is determined by like x squared plus y squared equals r squared or something. So one question is there any intuition for why the paper folding, the origami, is giving you cubics? Because I don't see anything that's intrinsically cubic about this. That's one question. And if you don't like that question, or if you prefer this other question, is there any way to see what sort of constructions you could do if you wanted to be able to solve things involving nth order polynomials? Like if I wanted to say, what set of construction rules should I write down if I want to solve quartics or quintics or sextics or something? Like it would be something beyond origami, but is there something you could say like, oh, these are the rules, and use these constructions, and now you can solve some fixed order polynomials or something? Is there something like that?
Oh yeah, I have answers to both of those questions actually. I'll start with the second one because I think this one is actually pretty neat. So as mentioned earlier, one method to fold a paper into thirds would be if you were to do something like this, right? And so this is not standard under the 7 axioms that I have shown. However, this is called a two-fold construction. So you can make it with 2 folds. Now, this is interesting because let's say I wish to solve a polynomial of degree n equals 4. I can do that with a 2-fold. And so I can, if I make 2 folds simultaneously, I can solve that. And in general, proving this would again be well beyond the scope of this talk. But if I have some polynomial of degree n, I can solve it with an n minus 2-fold construction.
Huh.
And so this is assuming that n is greater than or equal to 3, because you can solve quadratics and you can solve linear equations. I think that makes sense already, but not the quadratics, but the linear equations I'm sure you know can be solved. But with n is greater than or equal to 3, you can do it with in n minus 2 fold construction. What that means is, again, you make multiple folds simultaneously to do that. Okay, and the first question was, is there any intuition as to why you can solve cubics using these constructions and you cannot solve cubics with compass and straight edge? And so I'll talk about why you can solve cubics, which is, if you look at the 7 operations that I have, okay, operation 1 can give me a line, right? Operation 2 gives me perpendicular bisectors. Operation 3 gives me angle bisectors. Operation 4 is another form of perpendicular bisectors. Then operation 5 is again another perpendicular bisector. And so operation 6 though is different. As in, if we have 2 lines and we have, the slideshow explains it better. But basically, you can fold 2 points onto 2 lines at the same time. And it might not be immediately obvious why that allows you solve cubics. Because, But what I will say that would make sense is that you cannot do that with the compass and straight edge. There's no equivalent thing you can do to that particular operation with compass and straight edge constructions. And so that's the key to solving cubics. I don't think I answered your first question very well, but I think second.
I think you answered both. So you showed the extra ingredient in this construction that lets you do things you can't do with compass and straight edge. Yeah, the intuition for why it's cubic exactly is still slightly eluding me, but this general result that you say you could do with n minus 2 folds, you can solve nth order polynomials. That's surprising and interesting to me. So, I mean, if there's some notion of an n goes to infinity limit, if you consider like some set of rules where you can make arbitrarily many folds as you want at once or something, like an infinite number of folds or something, can you then solve transcendentals? Or like, because morally that should let you get a full Taylor series for any function. So you should be able to essentially construct any number that you want. I mean, has anyone looked at that, or does that not make sense?
It makes a lot of sense, actually. So, this has shown that you can construct whatever rational number you want, as I showed you with the grid making. So, if this paper is 1 unit long, I can make any rational number in length. And so, if we want a Taylor series for pi, for example, I think that's 1 minus a third plus a fifth minus a 7 plus ... And so, if I have 2 segments, I can add them, right? I can just line them up like this somehow, and then, okay, they got added. So now I have the sum. And if I have something else, let's say this is 1, and let's say this is a third, I can create a fold here that would then put this one there, and so you get this point. And this would be subtracting it. And so, if you can make any rational number you want, and you can add and subtract them, you can make a number like pi, for example, if you did this infinitely many times. Typically, one restriction we impose is that you can only do a finite number of operations. Because it's not at all practical to fold a piece of paper infinitely many times.
Yeah, but I mean, this is math, so who cares about practicality, right? I mean, if you just take a formal n goes to infinity limit, that's very satisfying, right? Because that's like saying, okay, if you allow yourself to make arbitrarily many folds at once, there's some notion of a n goes to infinity set of problems you can solve, which is like roughly anything which is computed by an analytic function, you should be able to construct using that set of rules. I mean, certainly it's not, not feasible physically with a piece of paper. I mean, there's some upper bound on how many times you're going to fold a piece of paper anyway. But I don't know. I find that very interesting. I'd never heard of that you can make arbitrary constructible or computable numbers or something if you allow infinitely many folds. That's kind of cute.
Yes. So yeah. Like if I had this paper, yeah, okay. I'm not going to present a concrete example of folding a paper into pi. That makes no sense at all. But okay, this is actually pi over 4. So I might be able to. But if I had a paper, it's like I can fold it into thirds like this, okay? And then I can make a fifth. I can line it up so that goes here. And then I can make it so that, okay, I've added my fifth. Then I can make a seventh, reline it up so that I can subtract a seventh. And it's gonna like, once you draw all the points, they'll make this like curve. And then right in the middle, you'll have your pi over 4.
Yeah, good.
So that would allow you to construct your transcendentals.
Okay, that's very cute. It's it's like some sort of physical approximation method. Like I mean, it's like writing an algorithm that's going to converge to some number, but it's much more tactile, right? Because you're imagining actually folding a physical piece of paper, which is cute.
Yes. Now that's like one of the reasons I like doing this. But you can construct square roots, for example. Okay, I have 1. Okay, so now I fold like this. And now I have the diagonal, and that's square root of 2, for example. So you can do these sorts of things like that.
Yeah, good. I mean, that's related to if you'll permit me a sort of qualitative, non-technical question, but I was just curious how you got interested in this subject, because you're clearly, I mean, much more knowledgeable about paper folding and compass and straight edge than I am, and I don't know how one typically gets into this, because it's not like part of the standard corpus of math stuff to learn. So like what drew you to this?
Yes. So the reason is I've always enjoyed making things with paper folding. Like as a child I used to fold all sorts of things. So I showed you the crane. There's somewhere in this room there's a large number of things that I have folded, and I just thought it was cool. And so what I realized is when I unfolded something, that there has to be something going on. Like if you look at this crane, right? We have lines. There has to be some sort of geometry that's going on. Like there has to be. I have lines. I have angles. So there's some math behind this. So I wanted to figure out what was going on, and so I did.
Yeah, good. I mean, this reminds me a little bit of, I don't know if it's related, but there's a guy at U Chicago in the physics department who used to be a string theorist, but now he's a biophysicist, and he was looking at how can you estimate essentially how much information an olfactory receptor in someone's nose could basically process. So like how many different smells could a receptor in the nose process? And the way he was modeling it was thinking like, oh, the receptor has some shape, and then there's some, smell molecule that comes and binds to it. And the amount of different, particles that it could detect is rate limited by how many different shapes could potentially bind into this receptor. And he was using some pretty sophisticated differential geometry to bound, the information content that could be packaged into a shape, basically, which is kind of like one of your origami folds. So, I mean, You could imagine asking something like that here for the folding, like, what is the information content of one of these crease patterns or something like this? Like how many, I don't know, how many qualitatively different structures could you be allowed to create with some fixed number of folds or something like that? I don't know if anyone's looked at that sort of combinatorics in this context as well, but it potentially could be kind of cute also.
It has been looked at, actually. In particular with respect to one pretty useful crease pattern, but it's like difficult. You'd have to read about it. I wouldn't be able to explain it in this setting. But what I will say, it's immediately obvious, is that if I have a fold, whatever crease pattern, every crease can take on 2 possible values, mountain or valley. And so I can upper bound the complexity by saying it's 2 to the n. But The actual upper bound is way lower than that because, as you saw, there's restrictions. This has to be equal to 2. That would reduce your upper bound significantly. And then there's other theorems that apply. So, for example, if I have this crane, I can draw the crease pattern. I hope I am drawing it correctly. Should be fine though. I'm not drawing it very neatly, but something like this. And the idea is, whatever your crease pattern is, I can color this perfectly with only 2 colors. And there's lots of other restrictions. People love this stuff because when you're designing a base for some origami thing that you want to make, so if I want to make like a dragon or something, I want the base to fold flat so then I can shape out the flaps into like toes or something, and that allows me to I have somewhere nice to start with if my base is flat foldable and it's not like this giant mess that makes no sense. So
So the point is, if it's flat foldable, then the thing corresponds to some planar graph, or I guess maybe you're drawing the dual graph where you're coloring the faces or the plaquettes or something.
yeah. So no matter what graph your crease pattern makes, if it folds flat, you can color it with only 2 colors. There's lots of other stuff as well, but as I mentioned, the alternating angles thing. I don't think that this talk is going to be though about just listing out all the possible restrictions that we have created. We still don't have a complete set of restrictions that you can apply that for sure guarantees if something folds flat or not. And it's actually been proven to be a problem that's NP hard. So if I have a crease pattern, I would need a lot of computational power to determine whether it folds flat or not if I haven't been given mountain valley assignments.
That's kind of surprising to me because I would have thought, given a crease pattern, to tell whether it folds flat, you essentially want to look for curvature, right? This is like some discrete metric on a surface, and you essentially want to see, is it flat? So the curvature vanishes. So it surprises me that it's NP hard, because I would have thought that given that sort of thing, well, let's see, what's the obstruction? So I guess you say it's probably harder than what I'm saying, because even if it's a tessellation of something with 0 curvature, then there could be some other obstruction, because there's these other constraints you said, other conditions for it to come from the folding. Okay, so I see. So I'm being too naive. I mean, it's probably easy to tell whether a given graph represents a tessellation of just a flat piece of paper, but whether that tessellation could come from the folding, I could imagine that part is NP hard. Okay, that I buy.
So if you look at the slide that I pulled up on my slideshow, this meets all the conditions that people have come up with, but it would not fold flat. You can't, I don't know why. It just doesn't work. And like all the conditions we have created can't explain why something like this would not be flat foldable. Like, I don't have mountain valley assignments here, but no matter how you would assign mountains and valleys, this will not fold flat.
That looks like it's a topological obstruction, though. Can you fold that into something that's topologically a sphere or a torus?
Not without adding new creases.
Well, yeah, I mean, you'd have to join, you'd have to glue stuff or something like that. But I mean, like, the obstruction, I mean, the point I'm making is that if you had something, something which is, you know, say, topologically a torus, and then you draw it as like, you know, a square or parallelogram with edges identified, and then you had some fold of the torus, you would never be able to, if you forgot about the identifications on the sides, you would never be able to make that flat foldable, because the genus of the torus is different than the genus of flat space. So that could, I mean, the topological obstruction is an immediate way of ruling out whether something is flat foldable, if it's something that you could only really do on a torus if you identified the edges. So is this of that form that with some identifications you could have you could have done it on some other topologically non-trivial space, or is that not known?
Well, it might be known. I have not looked into that, and I also don't understand this topology stuff very well because I haven't read about it. So
Okay.
that could be true, actually. But I don't know.
Yeah, that I suspect something like that might be true, but okay, that's interesting.
Yeah, might be. That is very interesting.
Yeah, it's like it's closely related to like the the Euler formula or whatever for the Euler character of a graph or something like that in terms of faces, vertices, and edges or something like that. I mean, you can very quickly tell if a graph is non-Plater by just computing its Euler character, and then you could see, oh, okay, it has the wrong Euler character, so it's really a graph on a surface of some other genus or something. This is basically the same thing, where like the vertices or the nodes of your graph are literally the vertices, where the lines intersect, and the edges are the edges. So there might be some game you could play with that.
Maybe. Yeah, I don't know how to do that though, so there might be something I look into.
Yeah, good.
Okay. Are there any other questions? I think I will wrap up about here, if there aren't.
Good. Well, if there's no other questions, then let's thank Eashan again for the very nice talk. I don't have a clapping emoji like on Zoom, but I'll just physically clap.
Yes. Thank you.
Good. Okay, I'll stop the recording here.